So in this session, we're going to look at second order differential equation. And then what we want to see are the methods that are used or that can be used to work out such differential equations. Now, generally, a second order differential equation is going to have a form like this. You're going to have a constant a, and then you have d squared this, and then you have dx here, and then you have b, and then this will have dy, dx, and then you have plus cy is equal to f of x. So this is an example of a second order differential equation. As you can see, this is second derivative, and this is a first derivative, and then this is just a function y itself. Now, there are two cases that we are going to start by analyzing. Okay, someone trying to join us. Okay, so this is an example of a second order differential equation. Now, there are two cases that we are going to analyze here. We're going to look at a case where the f of x part is equals to 0. And then in the next class, we're going to look at differential equation, second order, where the last part f of x is not equals to 0. So we're going to look at different cases in terms of this one as well. But for now, we're going to focus on differential equations in which that right-hand side f of x is equals to 0. How do you work them out? So prior to this, we saw how to work out different forms of differential equations, but all those were first order differential equations. So now we are moving on to look at the second order. Now, it turns out that if the right-hand side here is actually just a 0, the solution is going to have specific forms. We're not going to derive those forms. We're just going to demonstrate what they are and actually how to use those solutions. But one thing I'd want you guys to keep in mind is that if you have a differential equation and then it has solutions y1 and then it has another solution y2. So in such a case where two solutions are provided, well, you have to understand that even their linear combination will also be a solution to the same differential equation. So if y1 is a solution to a differential equation and y2 is a solution to the same differential equation, then even y1 plus y2 is going to be a solution to a differential equation, to the same differential equation. A good example where this was demonstrated is what we saw when we were just verifying whether something was a solution. Let me show you. So if you recall this problem, I think we had done it some time back. We had this differential equation, and then we were given 3 solutions, and we are asked to verify that those were actually solutions to the differential equation. So we started by first verifying that this was a solution, and then we also verified that 3x was also a solution. But look at that third case. In the third case, we have y is equals to c1, the exponential part, combined with the linear part. So when you look at this exponential part of this solution, you can quickly relate it to this, but the constant c1 here can take the place of 2. And when you look at the second part of this solution, which is c2x, can be related to the 3x here. So this just proves that statement where we're saying that if y1 can take this to be y1 is a solution to this, and y2, you can take this one to be y2. If it is also a solution to the same differential equation, then it implies that they are linear combination. When you just add them or subtract them, that should also be a solution. In this case, just adding them there, that should also be a solution. Okay, that aside. Okay, so generally, the solution to a differential equation is going to have a form y is equal to, and then here we can have a e, and then up here we can have the power mx. So this is going to be a general solution to a differential equation of this nature. But what you have to keep in mind here is this. Of course, this form can actually be verified, or it can be compared to the earlier case where I was showing you earlier on. I think so that was in the first part. Now, if you wanted to come up with this part, you can consider the same differential equation and try to derive it when the constant a here is actually 0. So if this part was 0, you have to observe that the differential equation that you remain with is going to be linear, and it can be worked out by separation of variables, and you're going to end up with a solution where it's going to have a constant a, an exponent to some other constant m, and the variable x. Now, this is how it is going to look like. That's just one solution. And as we saw in that demonstration I just showed you, the same differential equation can have multiple solutions. Now, in this case, if this is a solution, we can actually use this solution to figure out what one of the constants here is going to be. And in this case, we can actually target to try to determine what that constant m there is going to be. Now, it turns out that if what you have is a second order differential equation, like the way this one here is, if you are going to plug in this expression into this differential equation, what you're going to end up with is going to be a quadratic expression that describes what that constant m there is going to be. You can try it. You see, in this case, if you are going to plug in what the derivatives or what y is going to be here, in the first part, when you get the second derivative, you're going to get a, and the second derivative is going to have m squared, and then it's going to have e to the power mx. And then for the second part, second term, you're going to have b. The first derivative will only have an m here, and then e to the power 2, to the power mx. And the first derivative, this is just y, not a derivative. And for y, remember what y is. Okay, here we also have an a. Here, this is going to be a. And then you have e to the power mx is equals to 0. Quickly, you observe that the a here is present on all the terms it can go. And then the e, the exponent there, is also present in all the terms. And what you remain with is going to be a, m squared plus m. And then that's m. I can say bm plus, there is a c here. This c here, I think I skipped it. Let me place it there. So that c will still remain here. So you have plus c, is equals to 0. Now, this equation becomes the auxiliary equation, or the characteristic equation that will be used to determine what the constant m is going to be. Because when you look at this, this is just a quadratic equation, and we can now use this to find what the constant m in this general solution is going to be. Now, when you try to work out that expression to figure out what m is going to be, this being a quadratic equation, it's only right that you expect two values of m, so that in the end, when you try to find the general solution, you're going to have the first solution y equal to, you have a, then when m is one value, you're going to have e to the power m1x, and then this becomes the first solution. And then the second part can be seen when m takes that second value of m from that quadratic expression, and this is going to be seen as b. Then you have e. I'll use that as m2 here to show that that's the second value of mx. And then since these are solutions, remember what we said, if two expressions are solutions to the same differential equation, then even their linear combination has to be a solution. So that in the end, we can conclude that the general solution is now going to have a, e to the power m1x plus b, e to the power m2x. So this becomes the solution we expect to see for such a scenario. But of course, we want to keep in mind that a quadratic equation can have three cases in terms of its solution. Either the values of m are different and they are real, or the values of m are the same but still real, or the values of m, the solution to that quadratic, are imaginary. So those are the three cases that we expect to see when it comes to when we're solving a quadratic equation. But we're going to demonstrate these cases as we look at examples on how we solve second order differential equation. Any questions so far? So as you can see, when these questions are given in the exams, they don't really come with so many instructions. Like for example here, all you have is solve the following ordinary differential equation. All you see here is that these are ordinary. And when you look at the first one there, the first one is a linear differential equation, so its solution has to be obvious. We can look at it later on if you guys would want us to see how that one is solved. But the second one here is a second order differential equation. And this is what we want to see in terms of how we work it out. So let's just take this one. I'll copy this so that when you guys go through this document, you'll see how it's worked out. So this one, we haven't yet described how it's worked out. For now, let's just get this one. So let's see what kind of crazy we're going to see there. And we'll see how to work it out. Okay, so this is what we have. So we're going to concentrate on the second part there, and let's see what kind of values of m we end up with. So the first thing that you do when you have a second order differential equation, so of course, let's just write it down so that we understand very well what we are looking at. So this is the x squared, and then we have plus 5 dy dx, and then we have minus y is equals to 0. So clearly, the right-hand side is a 0, and this works because all the terms here do have a y. If this had, let's say, if it had a term that did not have a y, then this approach would have not been enough to work this one out. We're going to see differential equations which have such a term later on, and we'll see how we work them out. Okay, so next up, so we observe that the right-hand side is a 0, that is checked out, and then this is a second order differential equation. So next up, because it has fit into that criteria that we're describing, we need to figure out what A, B, and C, what they are going to be. In other words, I want to determine what A is, what B is, and what C is. Now, why do I need those values? Okay, I want to figure out what A is, what B is, and what C is. Now, why do we need those? We saw to say that they'll be key in figuring out what or how the auxiliary equation is going to look like, that characteristic equation. Now, of course, we need the characteristic equation for one simple thing. We know to say our general solution is going to have the form where A is a constant, then we have e to the power m1x, then plus b, another constant, then this is e, again we have m2x. Now we really want this to fit somewhere here, but in truth, this works when the values of m are actually real and they are different. If they do turn out to be the same, then we're going to see what modifications have to be made to this general equation so that again, they fit the solution. And if they turn out to be complex, I'm going to show you again another way that this can be rewritten so that that still becomes the solution. We won't derive those expressions, we'll only use them. And should we need them for this question, I'll bring them out. Okay, so this is what we have, that is our expression. And in this case, we see to say that our A is the coefficient of the second derivative, that is our A. Our B is the coefficient of the first derivative. If this were negative, you'd have to get that negative as well. And our C is the coefficient of that Y there. And in this case, don't forget, it has to go with that negative. So we have our A is 14. Our B is 5. And our C is -1. With this figured out, let's plug them into our characteristic equation. So remember how it goes. It's A, m squared, plus B, m, plus C is equals to 0. So in this case, what we have is 14 m squared plus 5m minus 1 is equals to 0. So that from here, we just have to figure out or work this one out, whichever way possible. So how would you want to work this one out? Can factorization work? Minus 14 m squared, and then 7 and 2 m. So it has to be negative. One of these has to be negative. We'll give it to the 2. The sum here gives us 5. The product gives us minus 14. So those are going to work. We can do it stepwise. 14m squared plus 7m. Then we have minus 2m minus 1 is equals to 0. From here, the common factor there, that is 7m. Then this is 2m plus 1. Then you have minus 1 here. And then this is 2m again. But this will be plus 1 as well, is equals to 0. So clearly, we have 7m minus 1, 2m plus 1 is equals to 0. So in the end, we have 7m minus 1 is equals to 0. M is equals to 1 over 7. And then the other side, we have 2m plus 1 is equals to 0. And then we have 2m is equals to negative 1, or m is equals to negative 1 over 2. So the two values of m have come out. Now we can plug them into our general solution. So the general solution, if you recall, this is how it looks like. So all we have to do now is plug in what those values of m. We have two values of m, so you can feed them in. So this is going to be y is equal to a e, and then m1. For m1, doesn't matter which one you give m1 there. So I can just give it 1 over 7. So you have x over 7 plus b e m2. So m2 will get negative half there, which gives us negative x over 2. So this becomes the solution. Now, in this case, notice that I have not tried to figure out what a and b, what they are. These are constants of integration. The only way you'd be able to figure these out is if you were given what the initial conditions are. Now, I think I haven't yet showed you guys how you work with the initial conditions. So I think I would like to take this opportunity as well to give you guys a question in which the initial conditions were given, so that you see how we can use the initial conditions to work out or to determine what those constants a and b would end up being. Okay, so any questions up to this point? Pardon? Seth, what are you saying? Okay, Seth, your network seems to be very bad. This is being recorded. I'll be able to share it with you as soon as the class is done. Okay. So having described the first part, let's quickly just demonstrate or point out how these solutions would look like for different cases, so that as we dive in to look at more and more examples, we don't get shocked by the things we're going to be using. Okay, the first example was kind of straightforward. It was able to play by the rules that we set earlier on. But what you have to understand is that it won't always be like that. Sometimes when trying to work out the auxiliary equation, am squared plus bm plus c is equals to 0. Sometimes when trying to solve this equation, what will happen is that the type of solutions you get for m, they might not be real and different. So they might not be real and different. First case, let's consider when m, when you actually end up with the same value of m, meaning that you have the values of m end up being the same. And in that case, what happens? Well, if you end up with one real value of m, so for this part, I am saying that you're dealing with a real solution, but that real solution, it's only one from that quadratic equation. You don't get two of them. So you only have one. Well, in such a case, that general solution where we had A here, e to the power m1x, and then you had b, and then you had e to the power m2x, it changes a little bit. If the values, or if the solution to the auxiliary equation ends up with only one solution for m, what would happen is that the solution would still look like this, but what would change is that this second term here is going to have an extra term here, and this is basically just going to be an x there, but it still maintains the same shape. So this is just what you guys have to keep in mind when you have when you're working with the auxiliary equation, and then you end up with the same or just one solution of m. In that case, just modify the general solution by just plugging in an x there. So again, as I pointed out, we will not try to prove this, but instead, we can just look at an example where that actually turns out to be the case. Okay, so consider an example where you have the second derivative there, and then let's say you have plus 10 dy dx, and then you have plus 25y is equals to 0. Again, when you look at this, it does fit the profile as we described earlier. The right-hand side here is a 0, and every term here has a y in one way or the other, either being differentiated or just on its own. So in this case, we can actually work this one out using the method that we described, identify the constants. Here, A is 1, there's nothing there. So A is 1. Then B here comes out as a 10, and then C comes out as a 25. So from here, we can plug them into the auxiliary equation. So you have m squared plus B gives you 10 there, and then C, so when you say plus, that's m here. So you have plus C is 25 is equals to 0. So this is what you end up with. Now, the question is, can you factorize this expression? Can you factorize? I think it's 5 and 5, because this is 25m. So I think you have 5 and 5. So 5m, 5m. So from here, you can clearly see that this is going to be m plus 5. And then this is also going to be m plus 5 is equals to 0. Now, in this case, you see that this is just m. From the first one, you have m is equals to negative 5. And from the second one, you also end up with m is equals to negative 5. So clearly, the two values of m that you're ending up with are the same. M is equals to negative 5, m is equals to negative 5. Well, since this is the case, the general solution in this case is going to have a, then you have the exponent of the first value, negative 5x, plus, now this is the modification that I was talking about. You're still going to have that constant b, but now we're going to plug in an x here, and then this will be e to the power, again, we have that negative 5x. So this becomes the general solution to that expression. Okay, now before we proceed to when the solutions of m are complex, do you have a question? Yes. So again, this is what I was saying. In this case, when you work out the quadratic equation, you have this and you have this. So from the first one, you get m is equals to negative 5. From the second one, you get m is equals to negative 5 again. So it's like m1 is equals to negative 5. m2 is also equals to negative 5. Yeah. Okay, so this is how it is going to turn out. So the last part is for when the values of m turn out to be complex. So let's consider when the values of m are complex. Now, what do we expect to see here? Well, for this case, we're saying that, okay, say you have the auxiliary equation, am squared. So others would call I call it the auxiliary equation. So, but you can also talk about it in terms of the characteristic equation. I think that's how others would also talk, refer to it. So you have am squared plus bm plus c is equals to 0. So when trying to solve this quadratic equation, sometimes it would turn out that the solution to this would be a complex solution, where I can take the first part to be maybe, I can just generalize this, where you have, let me just write it first the way it would be. You'd have b negative b plus or minus, then you have the square root of, so you can see I'm using the equation here, and then this would be b squared minus 4ac, and then you have over 2a. So when you make the substitutions and simplify, it is possible that it will simplify to some real number alpha here, and then plus or minus, and then the other part. So it's like the 2 over a, I split it to say negative b over 2a, and then negative b over 2a is what gives you that alpha. And then the other side, I have root b squared minus 4ac also over 2a. But it's possible that that second part will reduce to some term, but you have a negative under the square root. For such a case, you can isolate that negative 1 so that the negative is on its own, turning that second part into a complex or an imaginary term, so that in the end, you can isolate it as well and present it as the complex variable I, and then the last part of it can be taken as b. So you have the complex part to sort out the negative that can result there. Let me give an example for when you end up with maybe negative 16 here, and then maybe this is over some number, we can even say maybe over 2. So this would end up being presented as alpha plus or minus, and then the square root there, we can say negative 1 here, and then the square root of 16. So I've just isolated the negative 1 there. So the 16 here will square root correctly to give you a 4, and then that negative 1 will be seen now as our complex variable I. So you have 4 over 2, the square root of 16 is 4, and then 2 into that, this would end up giving you a 2 here. So this is basically what I'm talking about. So now, instead of just having a 2 here, in general, we know to say the root 16 or the root negative 16 could have been any number, but in the end, it turns out that you only have the complex variable I and some number b there. Now, so we're saying in this case, the values of m would reduce to this form. Now, for such a case, what happens? Well, you can now try to work with this general solution where we had y is equal to a, and then you have this is e to the power m1 plus, that's m1x plus be m2x. But when you look at this case, of course, you'd split this into the negative part and the positive part. What that would do is it's going to give you something, you'd have to end up using the Euler's identity again at some point. But all in all, this general solution can be simplified if you guys insist that we describe it. Would you guys insist that we derive it, or we just show you what you need? You guys don't want to insist? Let me show you what you need, and then you guys would decide if you want to see how that comes out. When you make the substitution, use Euler's identity where necessary. What you will see is that the whole expression will reduce to just something quite basic. It will reduce to just having e here, and then e will be to the power alpha x, and then open bracket. Now, this is where the constants will come in. Not necessarily the constant that you had here, a. The constants will combine in a way such that in the end, you have another general constant, A here, and then you have cos. Then this is where you're going to have that beta, beta there again. So beta, don't forget what beta is. Beta will have to be the expression or the value that turns out to be more like the coefficient of the complex variable I. And then x will be here. Then you have plus the constant b. And then now you're going to have sine beta x. So this is how the general solution would look like. Now here, this is what I was saying. Would you guys want to see how this came about, or you are comfortable with it so that we just see how to use it? So, okay, you want to see how it came about? Let's do that. Okay, it starts with this part. Having found what alpha is, or the expression for m, having found what it is, now the next part is you just have to make the substitution. Okay, so you just have to make the substitution here. Now, how would it go? Well, you know to say this expression here can be broken down into two values of m. M1 here will be obtained as alpha plus I beta. That is M1. And apart from this, M2 will be obtained as alpha minus I beta. Once you have those, now you can substitute them. So let's hold on to this. We'll see it when we reach it. So now you can plug in what M1 and what M2, what they are. So you now have A, E, where you have M1, you put alpha plus I, B, and this multiplies X. Then you have plus B, then you have E, then again you have alpha minus I beta. And then this has an X there. So of course, now you can distribute that X. And after that, we'll have to see again some rules of exponents. So you have E to the alpha X, and then you have plus I bx, and then plus B, and then you have E. This is X, that's alpha, sorry. Alpha X minus I bx. Okay, once this is done, you can now use the rules of exponents. And then what you observe is that this becomes A. Since the powers here are adding, it must have been that you were multiplying exponents there. So this is E to the alpha X, and then multiplying E to the I beta X. Plus, same thing there, you have B here, E to the alpha X, multiplying E to the minus I beta X. Now, when you look at that expression, e to the alpha X is common on both terms. This term is common on both terms. So you can factor it out. So this can now be seen as E alpha X, open bracket, A, E, I, beta X, plus B, and then you have E minus I beta X. So this is the expression that you now have. Now, how does this reduce to end up into this expression? So can you guys look at this? What would you use to make that transformation? Can you guess? Okay, so at that point, you'd have to use Euler's identity. Now, what does the identity say? I think we saw it at one point. I think it was in triple E when you're dealing with phasors at some point. Okay, but what does it say? Euler's identity there says that if you have the exponent of I, and then you have, let's say, beta X, this would be the same as, so in this case, you'd have cos. So let me remove the beta there for now. Let's say if you just had Ix, this would end up being cos x plus I, and then sine x. So in other words, it's the imaginary times anything here, but the anything will always be the argument of the trig ratios. So if the anything now is beta n than x, it will imply that this becomes cos beta x. And this would now be I sine beta x. In the same way, if now you have e to the minus I beta x, what would this be? If now you have a minus there, well, the first term doesn't change. This will just be cos beta x. But the second part there is now going to end up with a minus I, and then this is going to be sine beta x. So this is just what you have to keep in mind. So all we have to do now is plug it into our expression and see how it is going to simplify. So when you make the substitution and simplify, this is how you end up with that identity or that expression, that general solution. So let's see what you end up with. Now this is y. So that becomes y is equal to, we are not changing this one outside here. So we're keeping that one exactly the way it is, alpha x. And then now what we have inside is going to be, the first one doesn't have a negative, so it's going to take this form. So I hope you're starting to see how this is going to move. Then the second one, we're seeing a plus there. But don't forget, we do have that a multiplying everything. So I kind of left it out for a minute. So you have a here that is multiplying everything here. Then you have plus b also here, and b multiplies everything this side. Okay, I hope we'll be able to keep up with that. I'll write it better in the next part. Okay, so when this simplifies, you now have e to the alpha x, and then distribute the a, you have a cos beta x plus ia sine beta x, and then plus b cos beta x, then you have minus, that's I b sine beta x. Okay, at this point, you now have to group everything. Group what has what the imaginary parts together, and group the real parts together. So you have this, these are the imaginary parts, this and this, and then the real parts, you have this and that. So when you look at this, this is now e alpha x, and then the real parts, you have a, and then notice that the real parts are going to have a common cos beta x. Even here, cos beta x. So just going to be a plus b, and then cos beta x. Then you have plus, how about the imaginary parts? So the imaginary parts, when you look at them, again, they are also going to have a common sign beta x, and you're still going to have that a and b. So you can see you have I here, and then you have a minus, the b comes with a minus there. So this is b here, and then you're going to have sine beta x. So this is what you end up with there. Now, when you reach that part, I hope you're seeing how it simplifies. So finally, from there, you now have y is equals to e to the alpha x. And then the first part here, now this is where I was saying that the constants that have been plugged here as a and b, they're more like just the general ones, as in once everything is put together, that is what you're going to end up seeing there. Okay, so I hope you've got that part in check. Okay, so how do we conclude this? So we can now say that, okay, a plus b, since a and b, remember, they were constants in the first place, So even when you add two constants, you're just going to get some general constant. So if we want, we can say that we get the constant maybe C here, and then say cos alpha beta, beta x, I mean, plus we do have that complex variable I here, so I can keep it there. And then again, we can say that, okay, when we subtract A minus B there, so let's you get another constant D here, and then this becomes sine beta x. Now, when you look at the expression that we have now, it's closer to that term that we had here. So we can leave it like this and say this is the general solution, meaning that in the earlier expression that I wrote, only a complex variable there is missing I. Or we can say that D here will have to swallow that constant I, say D actually here, as in B here, also comprises of that complex variable. So if I make that argument, then I can say that, okay, I don't have to show that I. In that case, I would have to say that, okay, D here is actually equals to I multiplying A minus B. So I just keep in mind that D here then has to be complex. But I think in this case, I'll choose to keep that I present there. So I'll leave it there and just say D is a real number and only I is the complex variable. So meaning I'll leave this I to be present there. So this is how the general expression for when the values of M are complex in that characteristic equation. Are we okay there? Okay. So once you get how it goes, all you have to do now is remember how to use it. So for everyone else who maybe got tied up in the derivation, here is what you need in the end. So if you have a general quadratic, a general differential equation, second order of this form, so if you have a general differential equation of this form, second order, as you can see, the first thing you have to do is get the characteristic equation is equals to 0. When you solve the characteristic equation, if it gives you a complex solution, meaning you have M is equals to alpha here, plus or minus I beta. So you really want to reduce it up to this form. Once you reduce it up to this form, forget the magic that I just worked out earlier on. What you have to remember is that it implies that the general solution is going to look like this, e to the power alpha x. Again, forget that this is plus or minus. You saw how we derived that it didn't matter that we had a plus or minus there. That general solution already took that into account. So whatever the alpha here is, you'd have to plug it here. And then next open bracket, then you have some general constant A, and then the first has to be cos, and then beta x. Again, beta is the part that will be imaginary on your values of M. And then plus, as you saw in our derivations, I left out that I, so I can put the I there. And then you have B, and then this is sine beta x. So again, beta, it's still the same beta here that you'd have to plug in there. So again, all you have to do is work out that auxiliary equation. Once you work it out, you just have to remember the standard form of the solution. Is that okay? So let's see if we can find an example where this has to be done. Okay, I want to find one from an exam paper, but before I find one from an exam paper, let's see if we can work out something familiar to you guys that is readily available. After that, I'll check one of the papers I have to see if we can find anything that can be worked out. So in this example, I think I'm getting this from your notes, you guys. After that, I'll try to see if we can find something from the test paper or an exam paper. So we have something like this, and let's see how you'd work it out. So like I mentioned, get the auxiliary equation. So this is 1, this is 4, that is 9. So I have m squared plus 4m plus 9 is equals to 0. Once I have this, I'll jump right into the quadratic equation. negative b, so that is negative 4, plus or minus the square root of b squared, that is 16, minus 4, a is 1, c is 9. So I have this form. And then over 2a, that is just over 2. So I'm looking at negative 4 over 2, plus or minus, and then that is root 16 multiplying 16 minus 4 by 9. That sounds like a 36, is it? A 36. And then this also has to be over 2. So this is now negative 2 here, plus or minus. Now, when I get the difference there, what are we getting there? So I think that would be a minus 20. Minus 20 over 2. So clearly this is going to be imaginary. That is going to be an imaginary term. So I have minus 20 plus or minus. I'll put I here and say this is root 20 over 2. Now it's a positive 20 if you see there. Because of this I have put there. I hope you guys remember how that magic works. So once we have this part, it's now just a case of you sorting this one out. But if we want, we can actually keep this exactly the way it is. And if we did that, we can now say that this is our M. So from here, remember M in such a case had two important pieces, alpha and beta. So it implies that the negative 2 is our alpha, the root 20 over 2 is our beta. So alpha is negative 2, root 20 over 2 is our beta. With that in mind, the general solution will now have e to the power alpha x. So for alpha, we have minus 2x. Then open bracket, we have a constant, and then we have cos, and then this is beta. So for beta, I'll have root 20 over 2. Don't forget the whole thing is over 2. And then x here plus, and then we have b, I here, b, and then you have sine. And then we have root 20 over 2x. So this becomes the solution. Any questions there? Again, because this is a constant here, like I mentioned, you can choose the constant here to swallow that I. So say that, okay, D here is a complex constant so that it swallows that I for you. But this is still fine. Okay, so I think that is basically everything. Now, all we have to do is find an exam paper question that we can work out using this method. But everything here is really, really just the same. Wow. Yes, please.